going to figure out how exactly is a frequency calculated when they're designing an instrument. So whether we're talking a stringed or wind instrument, you're going to see where that actual frequency generates from. Next, we're going to talk a little bit about tuning as a group and what beat is. Following that, we're going to talk Doppler effect. So, to start with a few different terms here, frequency. When we talk about frequency of a sound wave, we talk about the pitch. Pitch is how our ear interprets a frequency. Is interpreted by the ear as pitch. Okay. Next up, loudness is the amplitude of the wave. Is how loud a wave is. Okay. So I could talk wavelength here, but wavelength really doesn't have any special interpretation in this case, because wavelength is simply how the medium translates the frequency or pitch that is being sent by an instrument. Okay. So first of all, let's just talk stringed instruments and what we call open tubed instruments. What's up? Okay. Thank you. Yep. That's regular physics. So string and open tubed instruments. So when I'm talking an open tubed instrument, what this means is an instrument that is open at both ends. So good examples of this are the flute. Say again? Yep. The part that's by your mouth is open. Yep. So the flute, the panpipes, bassoon is a good example. Recorder is a good example. Slide whistle is a good example. Oboe is closed. Right? Kazoo is not. The paper is closing that. Slide whistle has an open gap at the front where air comes in, just like a recorder. We'll get to that in a second. Oh, I'd have to look at a slide whistle. So we'll put that an asterisk next to that one. The part, so there are two things there. When we're talking about an open tubed instrument, we're talking, obviously the bottom end is open in some fashion, but there's a secondary way for air to come into the tube. So with the recorder or any of those, yes, you've got air has the ability of coming in or out via that small gap at the top. So you're playing by either blowing across the tube or by blowing into the tube, and there's an extra opening for the air to come in or out of. Okay? So stringed instruments, open tube instruments follow the exact same concept for producing sound. The idea behind them is that they're going to create resonance within either the air column that is within the instrument or within the string that's actually vibrating. That's my next step. So a string or open tube instrument, I know. It was good. I think so. Stringed instrument or open tube instrument cause, guys, the string or air in the instrument to resonate. When something resonates, that means that a vibration is introduced to that medium at the fundamental frequency of that substance. So if you start causing it to vibrate, it's going to create a standing wave within itself that builds and builds on top of itself. So when we had the rope out here and I started vibrating the rope and I created standing waves, what I was getting the rope to do was resonate with itself to get those standing waves to create and get larger and larger. Now there's enough friction in the rope that those additional waves dampened out, and it didn't just get larger and larger. But this is the same idea as, meaning vibrate at its natural frequency. As I change the amount of water in it, it changes the pitch of the glass. So basically what I'm doing is I'm bringing it up to a note that is within it's in a more reasonable range. I could get it to go without the water inside, but first of all, it's going to be lower. So I don't have any water in there right now. I could continue to add more or less to change that. No. This is Mr. Carney. Or the string that's attached to it to resonate. Okay, now we talked a little bit about standing waves last week, and there are notes posted on those if you didn't see them. Okay, but if I were to draw out what we're talking about, I'm just going to stick with a stringed instrument for now. And when we cause a stringed instrument to resonate at its fundamental frequency, we get a standing wave that looks like this. Okay, so what parts of the standing wave can you identify? Okay, crests, troughs, yes, but there are specific parts to a standing wave. Nodes. All right, we've got nodes at either end. And at the middle, antinode. This whole thing here is the antinode. All right, so when we produce the fundamental frequency of a stringed instrument or of a wind instrument that's open on both ends, what we're looking at is we're creating half of a wavelength within that instrument. So the fundamental frequency, meaning the lowest frequency that will vibrate and the one that you hear the most for that length of string, for that instrument tube, is the fundamental one. The mental wavelength for a string or open tube is 1/2 a wavelength from end to end. So if I wanted to actually measure the wavelength of the sound wave being produced, how would it relate to, say, the length of my string in this case? It'd be double the length of the string. Okay? So if I take a look at my wave equation for speed, v is equal to f lambda, I now know that lambda must be equal to 2 times the length of my string. Good with that idea? So based on the speed of sound, the frequency that I want to play, I can just simply take 2 times the length of my string, the speed of sound, and I get the frequency that I'll be producing. Okay. Now, obviously, this will vary based on the thickness of a string, based on the tightness of a string. So for stringed instrument players, you've got multiple different thicknesses of strings, and you adjust the tension of those strings in order to manipulate the velocity of sound within that string, thus adjusting the pitch because your length of the string is fixed. Make sense, string players? Okay, now the next part here is, let's say we take a, let's say well, it's easier for wind instruments, I suppose. Let's take two wind instruments, and they've got the exact same length, but they don't have the exact same sound. We can talk about a flute and a trumpet. We could calculate them out to be the exact same length, and they should produce the exact same frequency, but they do not sound the same, correct? No one's going to tell me that a trumpet and a flute sound the same, even if they're playing the same note, okay? Because they have different additional sounds that play within them, and the exact number of those, technically what we call harmonics, and the amount of each harmonic determines what the actual timbre of the sound would be. T-I-M-B-R-E, timbre. Yeah, you're probably right. What can I say? It looks like timber. All right. So, aside from just the fundamental frequency that's produced within this string, we could additionally have other harmonics. Those harmonics exist where we see other versions of wavelengths that fit within this section. So I could have my second harmonic here, which would fit a full wavelength, or I could fit my third harmonic in here, which would fit a wavelength and a half. Doesn't need to be, but usually they are. Let me rephrase that. Doesn't need to be, and it depends on the individual instrument that determines exactly what their amplitudes are for each one. The varied amplitudes is what determines the individual contribution of that frequency to the sound you hear. So the larger the amplitude of your harmonic, the more you hear that piece of the frequency as the sound is being produced. So, no, yes. Well, the note is the fundamental frequency, and the quality of the sound of the note, like whether it sounds like a flute or it sounds like a trumpet, is based on the additional pieces that go within that. Yeah. Uh-huh. Uh-huh. When you do that, you change the length of the string. Okay, so I do want to point out physics harmonic and musical harmonics are slightly different. Musical harmonics are just based on the key and thirds. Physics harmonics are literally every iteration of wavelength. So, yeah, they're slightly different. There is a calculation to go from one to the other. I'm not going to deal with it because we don't need to learn it. Yeah. Yes, the clarity and quality of the sound that you hear. Yes. All right. We can then actually see where these harmonics fit into a instrument sound based on this equation here, where we just take this value, and I want to make sure I'm writing it down right. Yep, over n, where n is the harmonic number. N is the harmonic number for a certain length of string, for a certain velocity of wave in an instrument, whether we're talking about a string or air in a wind instrument. We can determine the frequency of additional harmonics that would exist within this. So for this string, we've got our fundamental frequency, which is the full length, or double the length of the string. We've got additional harmonics, n equals 2, n equals 3, where n is the harmonic number, which is basically the next frequency that's going to contribute to the sound that that instrument is making. So harmonics are what are contributing to the sound the instrument is making, the fundamental frequency being the lowest of which is what you actually hear because it is the loudest of the set. N is the harmonic number. It is part of the equation. It's right here. Next set, closed tube wind instruments. Now, a closed tube instrument is basically going to be the rest of the wind instruments we mentioned. So any brass instrument, clarinet, let's see here, oboe, kazoo, a didgeridoo. So any of those instruments are closed tube instruments. They're closed tube instruments because one end is sealed off by the musician's mouth. Let's see here, closed tube instruments. When we're working with a closed tube instrument, usually, again, that's sealed off for most of us by a person's mouth playing on one end of that. We create a node at that end. And for the open tubes, and I should have drawn this up here for the open tube wind instrument, they actually only resonate when we have an antinode at the open ends. So the example I drew up above was a stringed instrument because we're fixed on the ends and we get a node on each. For an open tubed instrument, it's the exact opposite. An open tubed instrument creates an antinode on both ends. Here, for a closed tube instrument, we have one of each. A node at the closed end, an antinode at the open end. Node, antinode. All right, so following the same pattern here, we can take V equals F lambda, and we can say that V is equal to F times what portion of a wave do I see here? It's a fourth. This is a fourth of a wave because I'd make it just down to the crest or the trough. I don't make it back up. So I'm only got a quarter of a wave. So I've got 4 times the length of the tube here is going to create the wavelength of that sound. Additionally, I can create harmonics here, but again, I've got to make sure that they end in antinodes. So I could do something like this. I could do something like this. I'm eyeballing. If I was not, that would be pretty impressive if this was exact. Okay. But the important thing is that each one is ending at a node at the back end. Now you'll notice that I'm only drawing things in a certain iteration of wave. So my first one was a quarter of a wave. My second one went down to the bottom, so there's half a wave, and back up to here, that's 3/4 of a wave. My last one went down, there's a full wave, and is that a quarter? Yeah, I think that is. Okay, so, but either way, I'm working in odd iterations. I don't have half wavelengths here. I don't have half, I don't have fulls. Okay? What that means is that n still is the harmonic number, but for a closed tube, it only exists in odd harmonics. N is the harmonic number. But only exists for odd numbers. Harmonics are the additional sounds that are produced in addition to the fundamental frequency when a note is created or when that tube resonates. So n equals 2 won't exist. It won't exist because it would create a wavelength that would have a node here, and that node would cause it to cancel and not resonate within the tube. So that sound, while the wavelength could be produced, it wouldn't resonate, and therefore you wouldn't hear it because it doesn't have enough amplitude to actually produce an audible sound. It sounds correct, yes. All right. This being said, closed tube instruments, specifically things like, bass clarinet, produce a more pure sound than a stringed instrument or an open tube instrument because those ones will have additional harmonics that you would hear. You would hear fewer harmonics with a closed tube instrument. Yeah. How does what work? Those are not going to fall under the tube categories and have to do with the density of the object. Harmonicas, I think, are closed tube. Yeah. Yeah. Uh-huh. Has to do with the amplitude of those harmonics. So you're going to produce the fundamental frequency of that note, but if you're hearing two different notes within that instrument, within that random metal tube, what you've got is a harmonic that's amplitude is large enough that it can compete with the fundamental frequency. Yeah, you'll adjust both or possibly get rid of one. Yeah. Ooh, I'm not going to touch human vocal cords because that's next door, or rather a few doors over in anatomy, and that's just all magic. I got nothing. Next one is beat. I don't think we've got notes the rest of this week after today, right? Yeah, lab tomorrow, Wednesday, book problems Thursday, music and sound. All right, so first of all, I want to be clear, beat, when we talk beat in physics, we are not talking about how many beats per minute or what note gets the beat. We're not talking that idea. What we are talking about is a dissonant sound created by the overlapping of two notes. Okay, so anyone who has tuned another instrument by ear knows that pulsing sound that I'm going to talk about. When you get two instruments that are super close being in tune with each other, and you get that wah, 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 wah sound, and you adjust just slightly, and then you're in tune, that is beat. So beat is the constructive and destructive interference that occurs between two notes that are close in frequency. I do that to avoid it sounding like destructive. I accentuate that piece. Interference that occurs when two notes of nearly the same frequency interfere. So graphically represented, if I have some note with this as a wavelength, and I have some other note with a slightly different frequency, what we'll see is that when the two notes have their amplitudes, or sorry, their crests nearly lined up, really this would be for longitudinal waves, actually mean to use the word longitudinal here. Longitudinal waves, it would be where their compressions line up. We would get a louder note, which would be the portion of what sounds louder when you're trying to tune. And then when we start to get a crest and a trough lining up, or a rarefaction and a compression for the longitudinal wave, actually mean to use the word longitudinal there, we start to hear it get quieter. So that produces that wah, wah, wah sound when you are trying to tune two instruments that are nearly the same frequency. Last topic is the Doppler effect. Whoa. Yeah, that's okay, just so we've got that out of our system. Yes, this is the siren thing. So the Doppler effect is the observed change in pitch of a sound due to the relative motion between source and observer. The observed change in pitch of a sound due to the relative motion between source and observer. Okay. Everybody's had some kind of vehicle with a siren approach them, whether it's because they're passing them or because they're running from the cops. I'll let you keep that to yourself. So, because we have some of the individuals in this class that are in this class. So, when the siren vehicle approaches you, guys, siren vehicle approaches you, what happens to the frequency of the sound you hear? Does more than get louder. It's higher, okay? So the pitch will get higher when it approaches you. And as it recedes from you, what are you going to witness? Lower pitch, okay? So mathematically represented, the frequency that you observe, FO, is equal to the frequency emitted, FE, times the velocity of sound plus or minus the velocity of the observer divided by the velocity of sound plus or minus the velocity emitted. Okay, we'll get to how it's plus or minus. All right, so we just identified that if the siren's approaching you, this should be higher, correct? The observed pitch is higher, meaning that if we have a stationary observer, VO is 0, that this needs to be a ratio that is greater than 1. So make it so that the emitted sound has a lower frequency than the observed sound. Okay? So if I want this to be a ratio that's greater than 1, do I want to add or subtract the velocity emitted? Okay, if I add the velocity emitted, I get a larger denominator. This now is less than 1. Oh, okay. So I want to subtract this one, right? I want a lower denominator to cause this to be a greater than 1 fraction, and therefore my frequency observed will be higher than the frequency emitted. Minus VE for approaching sounds. All right. The cop's now stopped. You're coming up on the cop. As you approach the siren vehicle, that in this case our siren vehicle is stationary, you will hear the frequency increase. Okay? You're driving towards the vehicle that has the siren going. So we're going to see the same thing, meaning again, we want this ratio to be greater than 1. So in this case, I want to add VO. Plus VO for approaching observer. VE, velocity of the emitting object. VS, velocity of sound in this case. VO, velocity of the observer.